So question 12, the discrete random variable x has values 1, 2, 3, 4 and 5 and its probability distribution is defined as follows. Where we were given the probability where a is a constant. Show that a is 16 over 31. Well, the thing that we know here is that the sum of all the probabilities is always going to be equal to 1 when you add up all the probabilities. So if we think of the probabilities that we're dealing with in this question, then we're starting with A, and then you've got a half the previous probability each time, haven't you? So A plus a half of A, plus a half of that, plus a half of that. Where are we up to with that? So that was 1, 2, 3, 4, plus a half of that, 5. That's all got to add up to 1. We have got a 16th plus 2 16ths, so that's 3, plus 4 16ths, so that's 7, plus 8 16ths, so that's 15, plus 16 16ths, so that's 31 16ths of A is 1, so A is 16 over 31. And there we had it. We're then told the discrete probability distribution for x is given in this table. And so there we've got all the probabilities. Find the probability that x is odd. Okay, well, x being odd, that is what? 1, 3, so that's 4 31ths, and 5, 1 31th. Oh, where's that gone? No! This is going to be a struggle, isn't it? Oh, I know what I can do. Zoom out. Rub it out. Ah, seamless. Nobody on the video has ever noticed that anything went wrong there. So if we add that together, that is 21 over 31. 1 mark. Right. 2 independent values of x are chosen. 2 values of x chosen. Their sum is found. Find the probability that the sum is odd. So we're on part 3 now. The probability that the sum is odd. Well, there's 2 ways that can happen. That could be the first number was even and the second number was odd. Or the second number was odd. Sorry, the first number was odd and the second number was even. The other way around, anyway. So that's it. Right. We've done some of this already. So the first number, probability of x being odd, is 21 over 31. Therefore, the probability that x is even is 10 over 31. And then we're going to do it the other way around. So plus 10 over 31 times 21 over 31. And that gives us 420 over 961, I think. Is that right? 21 over 31 times 10 over 31. And we need to double it because we've done that twice. 420 over 961. 8. Right. Part 4. Do you want to just leave it until we're done? Part 4. Find the probability that s is greater than 8 given that s is odd. Now, we know something about this conditional probability thing. We've learned a little formula that says probability of A given B, probability of A and B divided by the probability of B. That's what we've learned already. So the top line is going to be the probability of the sum being greater than 8 and it being odd. Right. Oh, well, actually, that's not as difficult as it looks, is it? The chance of the sum of these two numbers being bigger than 8 and odd, well, the biggest these two numbers can be is 9. So bigger than 8 and odd, is that it? That's it. That's the only thing it can be. Oh, there could be 10, couldn't there? It could be 2 5s. So we've either got to get it to be 9. Oh, that's it. We've got to get it to be 9 in whatever way. The probability that S is 9 is the chance of it being both greater than 8 and odd. That's the only way it could happen, is for the sum to be 9. You're adding two numbers, and the numbers are 1 to 5, so the biggest it could be is 10, or 9, or 8, and so on. The chance of it being 9 is a 4 and a 5, so that's 2 over 31 times 1 over 31, or a 5 and a 4. So that can happen in two ways. So that is 4 over 961. 31 squared is 961. All that's left for us to do is to say that the probability of that happening, so we've done the top line, that is the probability of S being greater than 8 and odd, divided by the probability of S being odd. So that is 4 over 961 divided by 420 over 961, which is 4 over 420, which is 1 over 105.
Would you not do 10 values as well? As in, if you score 10?
If you score 10, it's not odd.
Oh, yeah. Silly.
There you go. Part 5. Sheila.
Can you just stay on that for a minute?
Yeah. I'll read part 5 while you copy that bit. Part 5 says that Sheila does something. She needs several attempts to start her car in the morning. She models the number of attempts she needs by the discrete random variable y defined as follows. Probability that y is y plus 1 is a half the probability that y equals y. Okay, for all positive integers y. Find the probability that y is equal to 1. Right, let's think about what this means. The probability of y being equal to 1, well, if we think of this the same way, it's set up in the same way as the previous one, isn't it? So you're starting with a probability of let's allocate it the same way. Let's say the probability of it being 1 is A. We're setting it up the same way as the first part because it's got the same format. Same format as the first part. So the probability of y is 1 is A. Probability of y being 2 is a half of A. Y being 3 is a quarter of A. Y being 4 is an eighth of A. Do you see how this is going? And this goes on forever. Now all of these numbers add up to 1. What we're supposed to notice at this point is this is a geometric series. It's a GP with first term A and common ratio a half. We're multiplying by a half each time. And the sum to infinity of this series is 1 because all the probabilities add up to 1. So the sum to infinity is equal to 1. And the sum to infinity of a geometric progression is A over 1 minus R. That's A over 1 minus a half is 1. That's A divided by a half is 1. So A is a half. So the probability that y is equal to 1 is a half. You had to notice that you were dealing with a geometric progression and work out how you could bring that into it. Sorry?
I didn't get how I got the marks for.
You got a half, and the mark scheme did allow, this wasn't detailed reasoning, so it was one of those ones where correct answer with no working out got full marks. There weren't many on the paper where that was true, but you'd arrived at it without particularly doing any working out to get there. You'd just come up with a half. So I gave you benefit of the doubt and assumed that you did know how you'd got it.
Well, I did, but I don't remember now.
Well. I got it. Part 6. Give a reason why one of the variables x or y might be more appropriate as a model for the number of attempts that Sheila needs. One of the models more appropriate, you could argue for either of them. So if you're going to argue for model Y, well, model Y is that the chance of her starting the car gets less each time, but she keeps on trying potentially forever. So X stops after only 5 attempts. So Y is more, you could say Y because X can't be greater than 5. And that would be a reasonable thing to say. Or you could say X. In fact, when I did this paper, I said X. And my reason for X was that any normal person, after you've made 5 unsuccessful attempts to start the car, is going to give up and walk or get the bus. So after 5 attempts, she would give up. And walk instead. You could choose, so you can see you could argue for either of those as long as you gave a reason. It did say give a reason why one of the variables might be more appropriate. So as long as you backed it up with some kind of reason, then you would get the 1 mark that was available there. And that's maths.